Hey guys, what's up? I hope all of you are doing well. So welcome to my YouTube channel Pratik Singh classes. In this video we are going to study Standard 12 Physics Volume 1 Unit 3 and Section 3.3.2, that is Tangent Law and Tangent Galvanometer. Here first we will start from the difference between ammeter and tangent galvanometer. Okay, then we will see what is the meaning of horizontal component of Earth's magnetic field. Okay, because it is related to this topic. If you have missed the previous video, please go and watch it. Okay, then in this tangent galvanometer we will see the working principle of it. Okay, then how it is being constructed and how does it function. We know very well that whenever we have two magnetic fields, okay, at an angle theta, and if we keep a bar magnet at that position of cross section, okay, the bar magnet will rotate towards the resultant direction of the two magnetic fields. Okay, so that property also is needed here. If you have missed the magnetic component of Earth, okay, please watch my previous videos. Okay, so without wasting our time, let us start our today's video, that is section 3.3.2, tangent law and tangent galvanometer. But before I start the video, I request you all to please subscribe my channel Pratik Singh classes, like and share and hit the bell icon. Fine. So coming to section 3.3.2. Alright, let us start our today's video tutorial. Okay, we will start from section 3.3.2, that is tangent law and tangent galvanometer. Okay, till now we have seen up to section 3.3.1. Okay, before I start this video, let me say you something very important. Okay, we know very well that the use of ammeter. Okay, ammeter measures the current in amperes. Okay, tangent galvanometer do the same thing. Okay, it also measures the current, okay, but not in amperes, rather than it measures current in theta value or deflection. Okay, how it is similar and how it is different from ammeter, we will see in this video at the end. Okay, till the end of this video, I request you all to stick to this channel Pratik Singh classes. Fine. So let us start section 3.3.2, tangent law and tangent galvanometer. Tangent galvanometer, as shown in figure 3.21, is a device used to measure very small currents. Okay, it is a moving magnet type galvanometer. Its working is based on tangent law. Okay, so here the first difference between a tangent galvanometer and an ammeter is that tangent galvanometer can measure the current even if its magnitude is in the order of 10 to the power minus 3 to 10 to the power minus 5. Okay, which is impossible in ammeter. Okay, and tangent galvanometer works on tangent law. Okay, this is very well given in standard 11th mathematics. If you haven't known that, if you haven't heard that or haven't studied that, you will see here later. Fine. So this is the figure of tangent galvanometer. As you can see here, we have two circular discs. Okay, one is this one. Okay, the another one is this one. Okay, these two circles are kept in such a way that they are concentric to each other. That means the center of this circle, okay, will lie somewhere here. Okay, and the center of this circle also will lie on the same point. Okay, and at that point where the centers of both the circles lies, okay, we have a magnet. Okay, a bar magnet kept there. Okay, that means the center of the bar magnet and the center of these two circles are coinciding with each other. Okay, and it is mounted on a table. Okay, and it is kept in such a way that its height, it will have three legs and its height from all those positions will be equal. Okay, and this is a very sophisticated device because it measures the current even if the magnitude of current is in milliamperes or microamperes. All right. Fine. Coming to tangent law. When a magnetic needle or magnet is freely suspended in two mutually perpendicular uniform magnetic fields, it will come to rest in the direction of the resultant of two fields. Okay, suppose we at one position we have two magnetic fields in two different directions which are perpendicular to each other. Okay, and if we keep a magnetic needle at that point, the magnetic needle will come in the resultant of both the earlier magnetic fields. Okay, so that is the tangent law. Okay, let me draw a figure for you. Suppose this is a magnetic field, okay, going from north to south or left to right, and another magnetic field lies like this one, okay. When we keep a magnet here, okay, at this position, let me change the color of the pen for clear visualization. All right, so if suppose we keep a magnet just at the center of the line crossing the magnetic fields, okay, then it will lie in the direction of the resultant of this magnetic field and this magnetic field, okay, if this is a bar magnet, okay. So this is called as tangent law. All right, now you have no doubt in this. If you have any doubt, you can ask your doubt, your queries in the comment section of this video, and every Sunday I will bring one questionnaire, okay, and I will try to answer all the questions if you will ask, if anybody will ask, and also the best innovative question person will get some goodies from my side, okay. While you are asking your doubt, write your name, your place of living, and your school's name, okay. Fine. Let B be the magnetic field produced by passing current through the coil of the tangent galvanometer, and BH be the horizontal component of Earth's magnetic field. Okay. So what happens here is, suppose, okay, the upper loop is a coil, means wires are wounded circularly here in this loop, as you can see the way my cursor is moving on the screen, okay, and current is passing through it. Okay, so because current is passing in this loop, it will create a magnetic field around it, okay, and another disc is kept here, okay, in such a way that it is lying in the horizontal component of Earth's magnetic field. So we have two magnetic fields here, one because of this loop and one because of this loop, okay. Because of this loop, the direction of the magnetic field will be towards the tangent of the Earth's magnetic field, horizontal component, and because of this, the current flowing and is creating a magnetic field around it, okay. Under the action of two magnetic fields, the needle comes to rest, making an angle theta with horizontal component of Earth's magnetic field, okay. So when we have a magnetic bar here, a bar magnet here, okay, it will act because of two different magnetic fields, one because of horizontal component of Earth's magnetic field and one because of the current flowing in this loop, okay, because of that magnetic field, okay. So after some time, when the bar magnet will come to rest, initially it will fluctuate, and once it will come to rest, okay, the direction of the bar magnet will be in the direction of the resultant of the two magnetic fields, okay, and that is given by B is equal to BH tan theta. Okay, now let us see the construction of this galvanometer. Tangent galvanometer, in short we write it capital T capital G, TG, okay, and now onwards we will always see only TG, not the full form, okay. So a tangent galvanometer TG consists of copper coil wounded on a non-magnetic circular frame. So as you can see here, copper wire is wounded here, and this frame, circular frame, is non-magnetic. So most probably it will be made of plastic or wood. The frame is made up of brass or wood, which is mounted vertically on a horizontal base table or turntable with three leveling screws as shown in figure 3.22. So as you can see here, we have three leveling screws, 1, 2 and 3, okay. It is made in such a way that we can adjust the height of this tangent galvanometer, okay, so that it will come exactly in the horizontal component of Earth's magnetic field, okay. This is adjustable screw. All right, the tangent galvanometer is provided with two more coils of different number of turns, okay. Most of the equipment we use in laboratory consists of 2 turns, 5 turns and 50 turns, which are of different thickness and are used to measure current of different strengths, okay. So what happens here is, in this same coil. Okay, in the same loop we have coils bounded of three distinct dimensions, okay, and also with different number of turns. You know very well that when we increase the number of turns, okay, the magnitude of magnetic field increases. Okay, suppose we have n number of turns in a coil, and if we increase the length of the coil or thickness of the coil, okay, then the magnetic field will also change. So that property is being used here. At the center of turntable, a small upright projection is seen on which compass box, okay, known as magnetometer box, is placed. Okay, so as you can see here, this one, this is magnetometer box. Okay, so it looks like this. Okay, at the center we have a bar magnet, and we have this angles from 0 degree to 360 degree, okay, mounted on this paper fixed here. Compass box consists of a small magnetic needle which is pivoted at the center such that the arrangement shows the center of both magnetic needle and the circular coil exactly coincide. Okay, that means the center of this loop, which is consisted with coils, okay, and the center of this magnetometer, okay, and the center of the bar magnet itself are coinciding with each other. Okay, a thin aluminium pointer is attached to the magnetic needle normally and moves over circular scale. Okay, so as you can see here, we have a circular scale here, okay, that is in angles, and as you can see a very small gray color line on this magnetometer. Okay, it is made of aluminium. Why aluminium has used here? Because it is very light and non-magnetic, and it is mounted over the bar magnet, okay, from the center. The circular scale is divided into 4 quadrants and graduated in degrees, which are used to measure the deflection of aluminium pointer on a circular degree scale. Okay, so here when this magnet will come, when this bar magnet will come under some certain magnetic field, it will rotate, it will change its position. Okay, and then this, because this aluminium bar is also fixed on this bar magnet, okay, it will change its position, and we have to see, we have to check, we have to measure at what position the magnetic this aluminium wire has come. Okay, in order to avoid parallax error in measurement, a mirror is placed below aluminium pointer. Okay, about parallax error you have learnt in class 9th. Okay, if you haven't, it is just like that when we measure anything with the help of a scale, okay, because the different position of eyes we have different readings. Okay, that is called as parallax error. Okay, to minimize that parallax error, we have a mirror below this pointer, below this scale. Okay, so that we can minimize, we cannot remove the error, but we can minimize as much as possible. While doing this experiment, while measuring the deflection in the galvanometer, we have to take care of some precautions. Number 1, all the nearby magnets and magnetic materials are kept away from the instrument. Okay, means if you have any other instrument which uses a magnet, okay, like your earphone, like your watches, okay, dialer, anything which contains magnet, you have to keep it away from this tangent galvanometer, because it is very sensitive. Okay, using a spirit level, the leveling screws at the base are adjusted that the small magnetic needle is exactly horizontal, and also coil that is mounted on the frame is exactly vertical. Okay, that means with the help of spirit level, we have to take care of the heights of this horizontal coil in such a way that it will be exactly in the direction of Earth's horizontal magnetic component. Alright, fine. The plane of the coil is kept parallel to the small magnetic needle by rotating the coil about its vertical axis. I am getting a lot of messages. Let me keep my mobile phone in silent. Just a moment. Once again, number 3, the plane of the coil is kept parallel to the small magnetic needle by rotating the coil about its vertical axis, as you can see here. Okay, so the coil remains in magnetic meridian. About magnetic meridian we already have seen at the starting of this chapter. Okay, now the compass box as shown in figure 3.23, okay, as given here, okay, is rotated such that the pointer reads 0 degree deflection. Okay, here the pointer means this aluminium bar, this aluminium line, okay, should always be in 0 degree pointings. Okay, now coming to its working principle, the theory. The circuit connection of tangent galvanometer experiment is shown in figure 3.24. okay, so coming to figure 3.24, so here you can see the circuit connection, how it is connected. Okay, and also you can see what are the equipments needed to do this experiment. Okay, fine. So here we have a tangent galvanometer, rheostat, 3-way switch, okay, key and a battery, okay, voltmeter, ammeter. Okay, so these things are given. Okay, and we have to do this experiment in the practical lab. Okay, and this you know very well that whenever practical will happen in your board exam, in your public exam, okay, one experiment will come for at least say 4 students. Okay, that means a group of 4 students have to do the same practical, so there you can help each other, okay, to get all the readings. Okay, but the connections you have to do there, but mostly in a school teachers do all the connections, students they have only to perform the action, perform the experiment and write the observations. Fine. When no current passes through the coil, the small magnetic needle lies along horizontal component of Earth's magnetic field, and in that situation, the aluminium bar will show 0 degree deflection. When a circuit is switched on, the electric current will pass through the circular coil and produce magnetic field. Okay, so when the circuit is switched on, the current will pass through this upper loop, okay, or the vertical loop, and because of that it will create a magnetic field around it, and because of that magnetic field, okay, the bar magnet will get a torque, and because of that torque its position will change and we can have the different reading. Alright, the magnetic field produced due to the circulatory electric circuit. Okay, now there are 2 fields which are actually acting perpendicular to each other. Okay, they are the magnetic field due to electric current in the coil acting normal to the plane of the coil, okay, and horizontal component of Earth's magnetic field. Okay, so here you can see, okay, that the magnetic field will be 2 there. Okay, one line vertical to the coil and one line horizontal, or you can say that in the direction of Earth's magnetic fields component. Okay, that is horizontal component of Earth's magnetic field. All right, coming back to the theory. Because of these crossed field, because we have 2 magnetic fields here, the pivoted magnetic needle deflects through an angle theta. Okay, and we know very well from tangent law that B will be equal to Bs tan theta. Okay, magnetic field here will be on this bar magnet will be given by Bs tan theta. When an electric current is passed through a circular coil of radius r having n turns, the magnitude of magnetic field is given by, at the center, B is equal to mu naught Ni by 2r. Okay, this equation we already have seen in unit 2, if you remember. From this equation and equation 3.30 we get mu naught by into Ni by 2r is equal to Bh tan theta. Okay, so here we have this B value and again here we have this B value. Okay, if you compare this both, we will get Bh tan theta is equal to mu naught into Ni by 2r. Okay, as simple as that. Let me erase all these things because it became a lot of dirty, doesn't look good. Just a moment. Okay, now nice. Fine. So in that situation we can write the horizontal component of Earth's magnetic field can be determined as BH is equal to mu naught Ni by 2R into 1 by tan theta, and here the unit is Tesla. Alright. Once again, the current in the circuit can be calculated from I is equal to K tan theta, okay, where K is called reduction factor of tangent galvanometer, where K is equal to 2R BH by mu naught into N. Okay, whenever detectors try to find out whether there is any kind of hidden electric circuit inside the wall, they use tangent galvanometer. Okay, they simply switch on the tangent galvanometer and hover the galvanometer near the wall, and whenever they see the deflection, they find out that there is some current passing inside the wall. Okay, and because whatever is the thickness of the wall, tangent galvanometer will deflect, because it is so sensitive that it can measure the current even if it is in milliamperes or microamperes. Fine. Sensitivity measures the change in the deflection produced by unit current, okay, and it is given by change in angle by change in current, that is d theta by di is equal to 1 by k into 1 plus I square by k square. Okay, tangent galvanometer is most sensitive at deflection of 45 degree. Okay, generally the deflection is taken between 30 degree and 60 degree. Okay, now let us see this example 3.9. A coil of tangent galvanometer of diameter 0.24 meter and has turn 100. Okay, that means N is equal to 100 and D is equal to 0.24 meters. Convert this into radius, that is R is equal to 0.12 meters. If the horizontal component of Earth's magnetic field, that is BH, is equal to 25 into 10 to the power minus 6 Tesla, then calculate I current, okay, when theta is equal to 60 degree. Okay, so we have diameter, okay, convert this into radius, then N is equal to 100, BH is equal to this value, okay, then theta is equal to 60 degree, so tan theta is equal to tan 60 degree is equal to root 3. So just use this equation. Okay, all the things we know very well. Okay, so we have the formula I is equal to 2RBH by mu naught into N into tan theta. Okay, see in equation 3.31, okay, we have BH is equal to, just a minute, mu naught into Ni by 2R into 1 by tan theta. So I will be equal to, just calculate in your mind, I is equal to, we have BH into 2R tan theta by mu naught into N. Okay, so as it is given here, 2R BH by mu naught into N into tan theta. Okay, just substitute the values, you will get 0.082 amperes, as simple as that. Okay, now the next topic is magnetic properties. Okay, about this section 3.4 we will study in our next video session. Okay, that is magnetic properties. Most probably I will upload the video about this today evening. Okay, I request you all to ask your doubts in the comment section. Okay, and on every Sunday we have a questionnaire. Okay, I will upload that also on either Sunday evening or Monday morning. Okay, and I request you all to ask your doubt in the comment section. Okay, the best question, okay, the person with the best question will get some rewards. Okay, the reward will be sent by the courier if you provide your address details in your comment. Okay, fine. While you are commenting, please mention your name, your place of living and your school's name, so that I will mention in the questionnaire video. Okay, I request you all that if you are new, please subscribe my channel Pratik Singh Classes. Keep watching. Okay, keep enjoy watching this channel. Keep learn something new every day, every time, whenever you watch the videos at Pratik Singh Classes. Okay, till next video, take care of yourself. Bye bye.